Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. I welcome you to the 14th lecture for the series of lectures on advanced computer architecture. Today, we will continue our discussion on instruction level parallelism after a brief review of the scoreboard approach for dynamic scheduling for enhancing the performance of instruction level parallelism. We will introduce a new technique known as the Tomasello's approach. In our discussion with the instruction level parallelism, we said that it is possible to enhance the performance of a processor by executing more than one instructions in a pipeline. However, we can enhance the performance of the system and avoid structural hazards, data hazards, and control hazards by using either software techniques or by using the hardware techniques. The hardware techniques exploiting instruction level parallelism work when dependence cannot be determined at the runtime. We discussed the scoreboard technique, which is based on the concept that we allow the instructions behind stall to proceed. This is accomplished by dividing the instruction decode stage into two parts, that is the issue and read operand. The issue is done in order, whereas the read operands may be done out of order. The structural data dependencies are checked at the ID stage, that is the instruction decode stage. The scoreboard also facilitates out-of-order execution, which results in out-of-order completion. In our discussion onto the scoreboard technique, we said that the scoreboard has three basic parts known as the instructional status, the functional status, and register result status. These three informations are maintained in three different tables. The scoreboard control unit checks the information from every stage as and when needed, and then it generates control signals to read the operands and pass on the information for execution purposes. We then found how the scoreboard can issue in order and execute out of order. I'll quickly go through a few slides showing what we discussed last time in this respect. We discussed that in clock cycle 3, when the multiply instruction was expected to be issued, it has not yet been issued because the second load and the multiply instructions both have data dependencies, and these dependencies are not yet clear. Then we found that in clock cycle 9, when the multiply instruction was expected to read the operands are read in clock cycle 9 by the multiply and the divide instruction, but the add instruction is not yet issued at this stage, whereas in clock cycle 17, all instructions has been fetched, the subtract instruction has completed out of order, whereas the multiplication instruction is still in the execution phase, and the operands for the divide instructions has not yet been read. However, we found that all these operations are complete in 62 clock cycles, where this table shows that the issue is in order. That is, the first instruction is issued in the first clock cycle, second is issued in the fifth clock cycle, third in the sixth, then in the seventh, eighth, and the last one in 13. Whereas the operand read and execution is out of order, and ultimately the final completion is also out of order. So with this much discussion onto the scoreboard, however, we found that the scoreboard enhances the overall performance of the pipeline. Now today I will give you another approach which was introduced by Tomasello for IBM 360/91 supercomputer about 3 years after the CDC 6600 was introduced. The goal of this technique was to enhance the performance without special compiler. For this purpose, Tomasello introduced slightly different instruction set architecture. In the IBM instruction set architecture, 2 register specifiers per instructions were used, whereas in CDC 6600, 3 register specifiers per instructions were used. Furthermore, in IBM, 4 functional point registers were used, contrary to the 8 functional point registers which were used in CDC 6600. So with these small modifications in the hardware, Tomasello introduced a new concept where the concept of reservation station was used and a new hardware was introduced, which is depicted in this diagram over here. This diagram contains a functional point operation queue. The function of this operation queue is that the instructions from the instruction unit are sent in this queue in order. Then the next unit which is used over here is the floating point adder and floating point multiplier reservation stations. These reservation stations include information regarding the operation, actual operands, and the information to resolve the hazards. This is the major difference in the hardware with respect to the scoreboard, which is used at a central position, whereas in this particular case, this control is distributed over the structure. In addition to this, there are 2 types of buffers known as the load buffer and the store buffer. Here, as you can see, that the load buffer can perform 3 different functions, that is, hold the components of effective address until it is computed, track the outstanding loads waiting on the memory, and hold the result of completed load waiting for common data bus. Whereas the store buffer has slightly different functionality. These functions are that the store buffer holds components of effective address until it is computed. It holds the destination memory address of outstanding store instructions, and it holds the address and value of store until the memory unit is available. The other different section is the design of the common data bus. As we know that on a normal data bus, the data and destination goes to the bus, whereas on a common data bus, the data and source, they come from the data bus. Moreover, the common data bus performs broadcasting operation, which means that it communicates with all the components of the structure. Therefore, in this particular case, all the results from the floating point units or the load unit are placed on the common data bus, which goes to the floating point register files as well as to the reservation stations and the store buffers. Now, with this much introduction about the Tomasello's structure, let us see what is the basic difference between the scoreboard and the Tomasello approach. In case of the control and buffers are distributed with the functional units in Tomasello's, whereas they are centralized in scoreboard. Functional unit buffers are called reservation stations and they hold the pending operands. The registers in instructions are replaced by the values or the pointers to the values in the reservation stations. This functionality is known as register renaming, and this technique is used to avoid the write after read or write after write hazards. We will talk about this in details when we will consider an application and an example during our discussion. More reservation stations than registers are provided in the Tomasello structure, and they are provided to optimize the functionalities which a compiler cannot do. Furthermore, in case of Tomasello, result to functional unit comes from reservation station over the common data bus, whereas in case of scoreboard, the result to the functional unit is made available through registers. So with this much introduction about the Tomasello's approach and the difference between the Tomasello and the scoreboard organization, we will now look into the actual data structure which is being used in the Tomasello's approach, and then we will extend this to the overall use in dynamic scheduling by using Tomasello's approach. Now let us have a look onto the components of the reservation station. The reservation station consists of different fields. The op field is one which specifies the operation to be performed in the unit. For example, whether it is the add or subtract or whatever operation it may be. Then it also has got a busy field, where busy field indicates that the reservation station or the functional unit is busy. Then it has got a field to specify the values of the source operand, and these values are defined by variable v and with the subscript j or k to specify the two operands. The other component is the source register value, which is to be written, and it is specified by using the symbols qj and qk. Note that a ready flag is not used in case of Tomasello, as we have been using in case of the scoreboard approach. Here, if qj and qk are made equal to 0, they are specifying that it is ready. Furthermore, the store buffer only have qi for reservation station producing the result. The other component of the reservation station is the register result status. It indicates which functional unit will write each register if one exists. Blank when no pending instruction that will write that register. The Tomasello approach is implemented in 3 steps. The first step is issue. Here, at this stage, we get instructions from the floating point operation queue. If reservation station is free, that is no structural hazard, then control issues instructions and send operands to the reservation station. This process is also known as renaming the registers. The second step is known as execution. Here, the operation onto the operands is performed when both the operands are ready for the execution purposes. The third step is known as the write-back step. The write-back step is performed when execution is finished. So this way you can see that there is a difference in the steps taken by the Tomasello as compared to the steps taken by the scoreboard approach. In case of scoreboard, 4 steps are taken. That is the issue, read operand, execute, and write back. Whereas in case of Tomasello, 3 steps are taken. That is the issue, execute, and write back. So no read operand stage is there in case of Tomasello. Now we will discuss this with the help of an example, how Tomasello can perform all the operations in 3 steps. For this purpose, let us consider this example program. The example program which we are considering in this particular case is the same as we considered for the scoreboard approach. Here you can see that the same instructions and same register names are being used which were used by the scoreboard. Here the first 2 instructions are the load instructions. Then it follows the multiply, subtract, divide, and add instructions. However, there is a small difference in the tables which you can see over here. The instruction status table contains 3 columns, that is issue, execution complete, and write result. Whereas the reservation station table contains 6 fields, that is the busy field, operation field, VJ, VK, which is the source addresses, and QJ, QK, which are the reservation stations for J and K. Along with this, the integers unit is specified separately by, which is shown over here as load 1, load 2, load 3, etc. So in this particular case, we are assuming that there are 3 integer units which are available, and the last section, as you can see from here, is the register result status, and this is the same as in the case of the scoreboard. Now let us see how this particular example program is executed step by step by using Tomasello's approach. Here you can see that in the clock cycle 1, the load instruction is issued. When the load instruction is issued, the busy is made equal to yes in case of the integer unit, and the location, which is 34 plus R2, it is loaded as the address value. In the clock cycle 2, the second load instruction is issued. Now here you can see the difference between the scoreboard approach and the Tomasello approach. In case of scoreboard approach, we were unable to issue the second load instruction because resources were not available. But in this case, as the integer registers are available, therefore the second load instruction is issued, and it is recorded here as, in the issue column, we have written value equal to 2, which means in the second clock cycle, the second load instruction is issued. And in the integer section, load 2 is specified as busy, and its address value is 45 plus R3. In the third clock cycle, the multiply instruction is issued, whereas the first load instruction completes its execution. Whereas you can note over here that in the reservation station, the registers names are removed. Instead of this, the name which is R within brackets F4 means that it is the register F4. Register name is written, and in the second operand, it is written load 2, which means it is the instruction name which is written instead of writing the name of the register. Whereas load 1 has completed and it is waiting to write the result into the destination register. In the fourth clock cycle, the first instruction writes its result in register F6. The second instruction has completed its execution, whereas the third instruction is in the execution phase, but it has not yet completed the execution. Whereas the subtract instruction has been issued. Here you can see that in this particular case, the add 1 is shown busy. The operation over here is subtract, and it is going to perform the operation onto an operand to be obtained from 34 plus R2 location. Here you can see that corresponding to add 1 in the reservation station, instead of writing the destination register names, the memory locations are written. Now you can see in the fifth clock cycle, the divide instruction is issued. The second load instruction has completed its execution, and its result has been written into the destination register, that is F2. Whereas multiply instruction is still in the execution phase, subtract instruction is also in the execution phase, and the divide instruction has just been issued. In the sixth clock cycle, here you can see that the add instruction has been issued, whereas the other instructions are in the process of execution, or they are waiting for their required operands. Here is the difference between the scoreboard operation and the Tomasello approach. In the scoreboard approach, the add instruction was not issued at the sixth clock cycle or at this stage, because it was observing a data dependency in this case. But here, even though there is a data dependency, the instruction has been issued because this is using the concept of renaming, and this renaming is done in the reservation station. Here you can see that the divide instruction has not yet started the execution. The multiply instruction still have 8 clock cycles to complete, whereas the subtract instruction has completed its execution. Then in the clock cycle 8, when the subtract instruction has completed the execution and it has written its result into the destination register, the integer registers are now available. They are not busy, whereas the multiply instruction still have to wait for 7 clock cycles to complete. The divide instruction has not yet started the execution because its operands have not been written into the proper location. Then in the 9th clock cycle, you can see that the multiply instruction still needs 6 clock cycles, whereas the divide instruction cannot start even up to this stage. At the same time, the register contents also showing the corresponding memory locations. As we mentioned earlier, the registers are now in this case representing the pointers. Then in the 10th clock cycle, the subtract instruction is complete, whereas the add instruction has also completed in the 10th clock cycle, but it still have to write the result into the corresponding register. You can also note here that the divide instruction has not yet started the execution, whereas in the 11th clock cycle, as you can see from here, the add instruction has written its result into the destination register, whereas the multiply instruction still needs 4 clock cycles to complete the execution, and the divide instruction has not yet started the execution. You can see the status is almost same in the 12th clock cycle and in the 13th clock cycle, whereas in the 14th clock cycle, the multiply instruction still have to go through 1 clock cycle to complete its execution. Now in the 15th clock cycle, the multiply instruction completes its execution and rest of the structure remains the same, whereas in the 16th clock cycle, the result of the multiply instruction is written into the destination register and the divide instruction starts its execution. As we mentioned last time that the divide instruction has a latency of 40, therefore it needs 40 more clock cycles to go through this to complete the execution. So therefore, in the 55th clock cycle, the divide instruction will need 1 more clock cycles to complete the execution, and in the 56th clock cycle, the execution of the divide instruction is complete, and in the 57th clock cycle, the result has been written. From this slide, you can see that the instructions are issued in sequence. From all the 6 instructions are issued in the first 6 clock cycles, but only first 2 instructions, they completed their execution in sequence, that is in the 3rd clock cycle and in the 4th clock cycle, whereas the other instructions, they completed their executions out of order. And similarly, the instructions are also completed out of order. Here you can see the comparison between the scoreboard approach and the Tomasello approach. You can note that the scoreboard approach requires 62 clock cycles to complete, whereas the Tomasello's approach requires 57 clock cycles to complete. Now this slide shows the comparison of Tomasello and scoreboard approach. The Tomasello approach shows that it has got pipelined functional units. There are 6 load, 3 store, 3 add, and 2 multiply or divide units. Whereas in the scoreboard, there are multiple functional units. There is 1 load store, 1 add, 2 multiply, and 1 divide units. The window size in case of Tomasello was less than 14 instructions, whereas in case of scoreboard, it was less than or equal to 5 instructions. The Tomasello does not have any issue on structural hazard, and the same is the case with the scoreboard, whereas the Tomasello allows to remove the write after read hazard by renaming, whereas the scoreboard approach uses stall. Similarly, for write after write hazards, the Tomasello uses renaming, whereas the scoreboard approach uses the stall. The other major difference is that the Tomasello uses broadcast result from the functional units, whereas the scoreboard uses the read-write registers. And the control of the Tomasello is through the reservation stations, whereas in case of the scoreboard approach, it is centralized inside the scoreboard. Now let us consider another example to understand write after write and write after read hazards elimination by register renaming. Here in this example, we want to multiply an array which is shown over here as contained in F0 by a scalar quantity which is contained in register F2. You can see it from this small program which is having a loop operation. Here we are assuming that multiply takes 4 clock cycles. We also assume that the first load takes 8 clock cycles, whereas the second and higher loads, they take 4 clock cycles. Now the question arises, why? We are assuming that the system is using a cache memory system. We will talk about the cache system at a later stage, but here I would like to say that cache is a fast memory which is used in the processor design to enhance the overall performance of the system. And in the beginning, we assume that the required data is not available and it requires relatively longer time to load the data into the cache. And this is known as the cache miss penalty. So this is why for the first load instruction, the load instruction takes 8 clock cycles and remaining instructions take 4 clock cycles. Now here you can see the last 2 instructions, that is the subtract immediate and branch if not equal 0. These 2 instructions are in fact written here based on the assumption that we are using branch taken. That is, if every time it encounters a branch instruction, we assume that it will be taken because this condition will be true. That is, branch if not 0 and the value is not 0 till the loop operation is completed. This we can manage by initializing the loop with a bigger number or with a number of cycles for which are the number of iterations which are to be taken up by this loop. So here we predict that the branches are taken, thus the reservation stations allow multiple executions of the loop by dynamic unrolling. Dynamic unrolling means that the 2 active iterations can be shown in continuation, as you can see from this slide. Here, this is the dynamic unrolling which is shown over here. That is, the first 3 instructions, they are repeated in the second half over here. So this means that when the 3rd instruction is executed, after this the branch condition is tested. However, as we are designing this whole system based on the prediction that branch is always taken, therefore the next instruction, which is the top load instruction, that will definitely be the next required instruction. So let us consider this example and see how this dynamic unrolling takes place and all the instructions are executed one by one. In the clock cycle 1, the first load instruction is issued. In clock cycle 2, the multiply instruction is issued. Here you can see that in the reservation station, the source locations have been mentioned as RF2 and load 1 is corresponding to the destination of first load instruction, which is F0. In the 3rd clock cycle, the store instruction is issued. However, you can note here that the multiply has no register name written in the reservation station. Whereas you can note here that in the 4th and the 5th clock cycle, nothing has been changed. Why? The reason for this is that during these 2 clock cycles, the conditions are being tested, and the conditional instructions, that is the subtract instruction and branch if not 0, they are being issued, but they are not shown over here. In the 6th clock cycle, the first instruction is reissued, which is the load instruction. Here you can note that F0 never sees the load 1's result. In the 7th clock cycle, the multiply instruction is issued second time, but this multiply 2 has no register name written in RS. In the 8th clock cycle, the store instruction is issued, and now during this time, the condition has been tested. The branch prediction was correct, therefore it continues in its normal mode of operation. Similarly, in the 9th clock cycle, now it is the time when the first load instruction has completed its execution, whereas in the 10th clock cycle, the result is written into the destination register, which is F0, and at this time, the second load instruction has completed its execution. The load 2, it was basically waiting for the condition to be tested, and if the condition is met, then it will accept the prediction, and then it has passed on this for the execution purposes, and the execution is complete at this time. Then in the 11th clock cycle, the second load instruction will write its result into the destination register. The first multiply instruction still has 3 clock cycles to go for the completion, whereas the second multiply instruction, that is in the second loop, it still has 4 clock cycles to go. Similarly, in the 12th clock cycle, the first multiply instruction still has 2 clock cycles to go, and the second multiply instruction has 3 clock cycles to go. So this continues, and in the 14th clock cycle, the first multiply instruction completes its execution. Therefore, in the 15th clock cycle, the result of the multiply operation is written in the respective destination register. Then, in the 16th clock cycle, the multiply instruction will complete its execution and will write back its result in the destination register second time. So, this way you can see that in the 17th, 18th and 19th clock cycle, it continues performing these operations, and it repeats the loop till the condition is not satisfied, and when the condition is not satisfied, the loop terminates. So this way you can see that it completes all its operations in 21 clock cycles instead of taking long times otherwise. So with this much discussion, we have now understood how the Tomasello algorithm works. The Tomasello algorithm performs much better as compared to the scoreboard algorithm, and this way this is a suitable technique which has been used in the IBM 360 computers for the enhancement of the performance. Here we have noticed that the Tomasello's approach is in many respects much better as compared to the scoreboard approach. In the Tomasello's approach, the use of reservation stations is quite useful in implementing the renaming technique to eliminate write after write and write after read hazards. Moreover, it has got lasting contribution in dynamic scheduling, register renaming, and removing the load store ambiguities. Now, at this stage, what I would like to suggest you is that you go through some examples given in your book Some more examples are also given in your class notes. Please go through these examples and try to solve them with patience, because they all need a lot of practice. However, I hope that at this stage you would have become familiar with the basic concept of dynamic scheduling. We will continue with the discussion on the instruction level parallelism next time, and we will particularly consider the concept of control hazards, which are very, very important from the instruction level parallelism point of view. So with these much discussions on to the dynamic scheduling for data hazards and structural hazards, I say you Allah Hafiz till next time. Thank you.